So hello. Okay, so today we will discuss more general, more realistic models of predator-prey dynamics, which go beyond the Lotka-Volterra model, and we will try to incorporate some biological facts that maybe will modify what is happening. Okay. So just to remember, we have written something like better this here. The Lotka-Volterra model, we use the V for the prey, and you use P for predator. So we have this minus, did I use, which letter I used? Alpha, yeah? Minus alpha times P times V. And then you had some key alpha P times V minus, I think was mu. P. That was the Lotka-Volterra system of equations. And if you look for what we call the phase plane, this was just something like this. You had the nullclines. I call this nullclines, but many people call this isoclines. And then they say the null isocline. Isocline is a line where a certain function, say v, has the same value. And if this value is 0, it's called the null isocline. Okay? But well, then a simplification depends a little bit on what people prefer. Call it nullclines. Okay, where here and then you had not circles, but you had closed curves going on here, this way. So these are called trajectories in the phase space, and over time you circulate here. Okay, every point is a point with a certain value of P or a certain value of V, and this changes over time. Over time you go on here on the curve, and then what you notice is that you start here, or start anywhere actually, you go on, and then you will come back after some time here, and then there is something which we call the period. The time it takes to go back to where you started, and this will go on and repeat itself, therefore you have a periodic oscillatory behavior. And we plotted these solutions. Of these equations, as we can write them in a usual way. So this was an example of the solutions which oscillate in time, but it's far from being a sinus or cosinus oscillation, which are the most common things that you see in physics, or first example of some oscillatory behavior like a pendulum or a spring are usually sinus and cosinus. Here it's not, but it has the same property that it goes up and down and repeats itself. Yeah? And then we saw that all of this could depend on the values that we put for the parameters. So these are more or less arbitrary values here, okay? Because I'm not even writing down the units of the values, okay? So it's just for illustrative purposes. And the thing that we also discussed is that if this E, which is the efficiency, which is the key here, If it's larger, then what you will see is that the oscillation, the prey and the predator have similar amplitudes. And it could also be that the efficiency is bigger than 1. Could it be? Or not? So, example. Okay, so it is usually when we have a mental picture of predation, we think of a super strong guy predating on a weaker guy. Okay, so typically a carnivore on herbivores and so on, and then obviously the efficiency is usually not bigger than 1 because it's a metabolic fact that you. But for instance, we also discussed that our predator-prey dynamics is describing biological facts that sometimes are not called predation. But for instance, parasitoidism. You have a parasitoid which lays eggs in the host, and then the eggs hatch, and then they kill the host, and they have a lot of, and then they become larvae and so on. So in this case, one host is being consumed, but a lot of larvae will emerge. So then this is a case where the efficiency is bigger than 1, and so we can also try to see what happens here if I put 2.0 here, for instance, and then run it. And what I see is that now the prey has an oscillation of amplitude which is bigger than the amplitude of the the predator has an oscillation where the amplitude is bigger than the amplitude of the victim, of the prey. Okay, so now there are many aspects here that we discussed yesterday and then we have also the faceplane if you want here, and I'll run it again also, and this one. Okay, so very ugly thing, but there it is. I mean, it starts somewhere and then it goes and circles. Okay, and okay, here you have several initial conditions. Okay, never mind. So, okay, so we discussed the problems which such a situation presents from a theoretical point of view. Which, from the theoretical point of view, is a system which is called structurally unstable, in the sense that what we saw is that under small perturbations, for instance, you would never see actually the periodic motion because you get trapped. If you go from here to here, you get trapped on this trajectory. When you go from here to a perturbation, and you go here, and then you are trapped here. And this has a different period than this one. So this would be very strange. And then you also know that, for instance, in the examples that exist about in the field, in this kind of Arctic regions where you have oscillations. Why Arctic regions? It's usually because trophic interactions and trophic webs in the very cold places like this, like Arctic, are usually smaller number of species, which is relevant, is smaller, for instance. And then sometimes you have a predator that, even if it's a generalist, that has a strong preference for one of them, and this one maybe will be like the lynx and the hare. Okay? So, and then what we see at the oscillation period is the same, irrespective if you are in a certain region or another region, and these are geographically not connected, Therefore, there are two subpopulations. They have the same period, but they don't have the same number of individuals. So they should have, through Lotka-Volterra equation, they should have different periods, but they don't. So that's a problem. And then there's another thing, which we didn't discuss, but obviously there are situations of predation is widespread phenomenon. And not many times you have an equilibrium between predator and prey static. You have some level of the populations which is it's nearly constant. I mean, it fluctuates through perturbations, but it's nearly constant. It's not cycling. And Lotka-Volterra has always cycles, and that's also not true. Right? So we need to put some more. We need to modify these equations in some sense. And our guidelines to modify the equations and to build new models will always be, okay, let's just try to include a new biological fact. Okay? So that's clearly important, because you could also just try to fabricate mathematically something that shows you some behavior. Okay? But just fabricating mathematically something will lack biological realism. Okay? So let's start with something that we can do, which has at least some biological justification. And well, the most obvious thing that you can ever do is say, there is no such thing as exponential growth forever, therefore there should be a carrying capacity in the system. Okay? So this will result, I don't have even to write the system again. Okay, I will erase this one. Okay? Just put a carrying capacity here. Okay? Easy, easy, easy. Simple modification, put a carrying capacity. Okay? So now this carrying capacity will modify the null clines. So remember, the null clines are the points where dv dt and dp dt are 0. So dv dt equal to 0 will give you r times the v I don't need to use, because I'm supposing v is not 0. Therefore, I can cancel, because if I just write something equal to 0, v is not 0 and it appears in both terms. I just can disregard it. So r times 1 minus v over k minus alpha p is equal to 0. Okay? And the other one is not modified. dp dt equal to 0 gives you just that v is equal to mu over chi alpha. And if I now plot this and this here, I will have here v, I will have here p, and v equal to alpha key over mu. It's just the same line we had before. Exactly the same. Okay? This is a constant value of v. Now here, this would say that p, if you just write this like, let me put it here, that p is equal to r minus v over k, r1 over k divided by alpha. So this is a straight line. Okay? It is a straight line, and this will be something of negative inclination. Will be something that will, okay, we can see where it will, if I take v equal to 0, this is r equal to R over alpha. And if I take P equal to 0, then V is equal to K. So this is something like that. Okay, so these are the null clients. Then you will have, you can do all the analysis with the errors. Yeah. Here's one.
I didn't quite understand why you would add the carrying capacity only for the first equation and not in the second also.
I'm supposing that still the same situation where the predator is a specialist. Therefore, we only have birth of predators, this term, due to the consumption. Right? If I add a carrying capacity here, which I can do, I'm supposing that there is something else
making top down.
That the regulation. So here now with the carrying capacity, the regulation of the prey population is top down by the predator, but also bottom up because there is some consumption of resources that we are not putting explicitly, but it's a carrying capacity. And now and I continue to consider that the predator is regulated only by the population of the prey. Therefore, it's bottom up from the point of view of predator. Okay? So, having another carrying capacity would say that there are still some other things that that can be consumed. So, okay. So let me take this here. So you can do the same thing with all the, which I don't want to do because, again, all the explanation, which is this thing. Because it's exactly what we did yesterday, okay? But instead of having an intersection like this, it's not only just you have an inclination, okay? Therefore, you go from here, and you will also have cycles. But point is, will the cycles close? I mean, the tendency is to go from, you start here, you get here, here you get upside, and you go this way, and then you get back. So the cycling behavior seems to be there. But now, with this different null clients, maybe, it could be, that instead of having a closed curve like I have with Volterra, maybe the curve will not close. What will happen? Okay, and so this intersection here is it's a fixed point. Right? So the question is it stable or not? Okay? So this cannot be done graphically, just graphically, because in order to do this, you would have to actually use something that would be the size of this errors, and then it becomes tricky, and it's better doing something else. And so, what is something else? Let's just find a solution by numerical methods and see what happens. Okay, and then we can also plot. We want the carrying capacity, then the phase plane. Okay, so let me see. So this is a very simple. If you have had the Lotka-Volterra equation with Renato, yes, I think so, on the computer in the computational part. So it's just changing the expression of the equation by putting a carrying capacity, and then you postulate something about the value of the carrying capacity. Okay. Now, so we have the same system. You see that we have now a new parameter, which is the k, And then you have to take a look what happens in this case. Okay? So, and then we will also be interested in looking how the solution behaves in terms of k, large k, small k, and take a look. Without any k, we know that what you have is oscillations. That's it. Volterra oscillations and so on. But now we want to see the dependency on k also. So we start with k equal to 100, and the equation is just the same equation as before, but you see that there is a term here now with this, which is the, okay, you run this. And, okay, so what you see here, let me see, it was not the best point, with a carrying capacity of 100, but let us plot only 100. So it's better like this. Okay, oscillations with decaying amplitude, and after some time you are very close to a fixed point. Okay? So when you look at this, you have oscillations, both prey and predator oscillate, but very quickly the amplitude goes to a very small value and goes effectively to a fixed value, about 20 and about 3 or 4. Okay? So what happened is I get over time a fixed point which is approached through oscillations. So we can plot the phase diagram for this, which is not difficult. Okay? And here we are. You started here. You go and you spiral, and you get to a fixed point. So you have transient oscillations, but at the end of the day, you don't have sustained oscillations. You go to a fixed point. Now, let's see how the carrying capacity affects these things. It will not be so fun. If I put a very small carrying capacity, let's say 10, if I put a small carrying capacity, then we should be, so when we had the Lotka-Volterra original equations, I didn't have a carrying capacity, which is the same to say that the carrying capacity was infinite. Therefore, V over K, with K being very large, then it's a very small number, and then you could neglect it. Okay? Now say that the carrying capacity is small. Let's try with 10. Okay? So you see, it did not even oscillate because it's so small that the motion gets kind of damped. Okay? And you see that it's in this case, the prey is almost at the carrying capacity, and the predator actually is gone. This is not exactly mathematically, but it's very small numbers. Okay, here. So biologically, this would be saying that it's a biological zero, and then obviously there's no fun. But you can also plot this other one. So we saw with 10 and with 100, and then I could say, okay, now I want a really big one. Okay, let us put 1,000. So this should approach to, you would expect to have more and more oscillations. Okay? Why? Because large carrying capacity is near the limit where the Lotka-Volterra equation should be valid. Okay? So you run this, but you see lots of oscillations, but they are still going somewhere. So I run it for 100 times that, let it put 500, oh, too much. And then it becomes clear that you oscillate a lot in time, but you go to a fixed point. Nice, yes? And just to mention the fixed point, for instance, if you look at prey here, the carrying capacity was 1,000. Okay? But it's not even near 1,000. Okay? So it does not go to carrying capacity. It goes to an equilibrium between predator and prey, which has different values, which are the values of the fixed point. Sure. So, and if I plot this here, you have this nice thing, lots of circles, spiraling, and then you have a problem with the size of the pixels here. You cannot anymore distinguish here in this side, but it's going to spiral its way down there. Okay. Okay. So that's all with this equation. Again, there is no other thing, and the result is that you can end up at a fixed point. So, okay. So here's Mike. You have already the mic. Good.
Does the amplitude of the oscillation decays exponentially?
Good. No idea, actually. No idea. So what in order to do this, you have to try to make an approximation theory in which you write, you suppose that you have you have a function which oscillates with a constant amplitude multiplied by a function of time, which is the amplitude. And then see if you can get exactly, you won't get it, but then you can try to see, for instance, at least maybe with either very big or if you start near the fixed point or something like that, and you have to try to do some asymptotic analysis with this. I have never seen this, but it's actually a nice question if it's exponential or not. Okay.
Yeah, because if it is exponential, then there should be a parameter that dictates how fast this decay, and I was interested in knowing how this connects with K and alpha and R.
Yeah, so it has to have some relation with K. Okay, but empirically, I mean, looking at the computer, it has something to do with the K. Okay, so but how exactly, I don't know. But this should be done with asymptotic analysis, with supposing some parameters are small or big, and try to do something. Okay. Yeah. Not trivial, but maybe it's doable. So, okay. Now, we are not happy anymore because there are cycles and nature, and this thing says there is no anymore. All cycles are transients in this case. Okay, only during a certain period of time you see oscillations, but they don't have a fixed amplitude, and they have a decaying amplitude and will ultimately go to a fixed point. Okay, so you could say, well, maybe it's like that, and maybe there are other explanations for the cycling that we see with fishes or with lynx and hare and other situations. That could be. But well, we can still modify this equation, which is what we discussed yesterday. Remember that we originally rewrote, instead of putting v here, it was a function of V. And this function was called the functional response. So remember when we wrote this in this way, we want to keep already this guy here. So it's, but we had something which was an alpha times p. Okay, by p times a function, which could be a function of v in p, which we suppose that this function is just alpha times v. And then we had this thing. It's exactly the same thing. We had this one. So, and we discussed that, therefore, let's remember. This f, what is this f? If I have one predator, that's the number of prey consumed by one predator per unit time. Okay? That's the number of, the variation of the number of prey per unit time. This is the number of prey which has been consumed by one guy. Okay? Typically. So, and we suppose that this was just proportional to the amount of prey. And this was what we discussed at the end, as an assumption that this predator is absolutely voracious. Okay? I should have, I will always forget this. So it's absolutely voracious. There is no limit for the predator to consume prey. And we know that this will usually not be true. Okay? So we want somehow to study the effect. How could we express mathematically the fact that a predator becomes either satiated, or, which is very similar, either it has to manipulate the prey. In both cases, this means that the predator will spend some time not preying, not looking for prey. It will stop. It will be satiated, and then it will not go on the hunting, and or it's still busy manipulating. Okay. This is more or less the same because you can also think that satiation comes from manipulation, but not manipulated with hands on it, but it's digestion and so on. During some time, the predator will stop looking for prey. Okay? So, yes.
Is there a reason for that plus sign there on the first equation, or is?
Oh, this is a reason is that it's wrong. Reason it's wrong. Okay. Thank you. So, well, technically, it could be maybe correct if I just put minus alpha into the f, but okay. But it's not the usual way. Okay. So f has to be positive. Okay, so having done this now, I will give you an argument how to do this, which is not very rigorous, but is convincing. Okay? So, say, let's look at predators, and these predators are very simplified predators. Right? They do only two things. They look for prey, and then they stop and manipulate the prey. Okay, that's the life of this predator. Okay, so the time for the predator is divided between time for searching and time, which is usually put with S for handling. Okay, handling time. That's actually the technical term, handling time. So time goes on, and the predator is it's either searching or it's handling. So now the handling time is some fixed time. It's the time the predator takes with handling, which can be also the time the predator stops to look for prey because he is satiated. So there's a typical time. Okay? Obviously, more rigorously, this would be a distribution of times. Okay? But let's say that's the average time. That's the average time to handle one prey. But if you have more preys, it will have we will suppose just that this is something like this: the number of prey. It's proportional to the number of prey. If I take 1 hour to handle one prey, I will take 10 hours to handle 10 prey. Okay? So, which is obviously also an approximation and so on. Okay. Well, so now the time for searching comes. So this is the number of prey which is being consumed. Okay. Number of prey being consumed. Okay, I would rather. Okay. Just remember, this is the time of the number of prey being consumed. It's not the total number of prey that are available. So maybe we change this to n. Okay, not to confuse exactly. It's not exactly v. V is the total population of prey. So what we want is the number of prey being consumed. So I will change the notation in order to make this distinction. Okay, the number of prey being consumed, and number of prey being consumed. So okay. On the other hand, the number of prey that is being consumed, okay, should be something which is like some constant, which we call alpha, okay, times the time it takes to find one, searching time, okay, times the number of total preys. Okay? So the number of prey being consumed will depend on the time the predator searches, but this he will find more prey if there are a bigger population of prey. Okay? So we will consider this is also something which is linear with the population of prey. Therefore, I can write the time it takes to search is the number of prey being consumed divided by alpha times the total population of prey. Right? Yeah.
This alpha is the same as before.
It will turn out to be. It will turn
Ah.
out to be, but for the time being, it's not. But then we
Okay.
will see it will be connected.
Yeah, thanks.
So, for the time being, this is just a constant that's here, and well, just to have an idea, we have now new constant here, which is it's connected to the handling time, and this alpha is connected somehow to the time for searching. So now I can write the time is equal n over alpha v plus h n. Okay? which can be written, putting n in evidence, as, I will use it in this way, which is 1 plus hash alpha v over alpha v. Okay? I multiply alpha v here, and I put it in evidence, and then I have 1 plus this. Okay? Now, the number of prey being consumed by unit time will be just n over t. Okay? So we want to write down n over t, which is prey per time. Okay? So this part is obviously not so rigorous because I'm saying this is somehow connected to the derivative. Okay? And we didn't actually do it with differential times and so on. So n over t you can get from here. N, okay, over t will be just equal to this, I think, alpha v over 1 plus hash alpha v. Nice. So this is the functional form. This is our f. Okay? Remember, f is the number of prey being consumed by unit time by a typical predator. Okay? So, and I now just divided the time for my predator, just a minute, for my predator into two different activities, searching and handling. I write the handling time as proportional to the number of prey which is being actually consumed, and I say that the number of prey being consumed is the time of searching times the number of the total population of prey. So it's okay. So and then I just do the algebra here, and I calculate n over t, and I say this is the functional form, functional response, which gives you this. Okay, question.
Just one thing I didn't understand. The th equal hn. Th is a handling time, I can understand that, but what is h exactly? How is it?
So this is the time it takes to manipulate a certain number of prey.
So it's still time.
It's a time, handling time. Not a rate? No, in this case, well,
It's because handling time is th, so th is equal th multiplied by n.
T is the time it takes to handle one. Okay. That's true. Okay. So if n is equal 1, th is equal to h. Okay.
Okay, but
Okay.
what is h exactly?
H is the handling time. It's called handling time. The handling time is like the unit handling time. Okay? The time it takes to handle one prey, here, but one, this is h. Okay? The time to handle one prey. Now, the time that the predator spends handling prey, it's the unit time for handling a prey times the number of preys. Okay? Okay? So it takes, say, 1 hour to handle a prey. Then h is equal to 1 hour. But now I have 10 preys, and it will take 10 hours. That's it.
Maybe you can call it handling time per prey. So
Yeah, I mean, okay, the usual form is handling time, but okay, that's the handling time for one prey. Okay? So it's okay? So it has units of time. Okay? So, okay. And actually, we can also look for what's the alpha, okay? Alpha has to have units. If you look here, okay, you have V and you have P. Both of them are population sizes, okay? So alpha f will have to have dimensions of 1 over time. Okay? In this case, this has to be dimensions 1 over time, means that you have already a population here. Therefore, alpha must be something which is time, 1 over time times population. Okay? And that's okay. If this is 1 over time, then you see it's 1 plus something. All of this has to be without any dimension because the 1 doesn't have a dimension. Okay? So alpha has dimensions of 1 over time over populations. Okay? So, and that's usually this. So it turned out to be the same alpha. Okay? If handling time is 0, which is the limit from the previous functional form, if handling time is 0, that is the same alpha that we had before. Okay? So that's why I called it alpha. Okay? So now we have an equation. And it's curious because, you know, when physicists or mathematicians look for differential equations, it's very, very, rare. It's really seldom that you look at equations which have fractions of the function in the equation. It's kind of, when you see this for the first time, you say, oh, this is ugly. No, usually you have polynomials or something like that. So it is as it is. So we will have to handle this handle. We have to study this equation. And so this is a modification of the Lotka-Volterra equation, including handling time and carrying capacity for the prey. Okay? So this system is called the Rosenzweig. McCarthy equation. And this is more or less what people would call the standard model for predator-prey dynamics. It's still general because we have taken into account things that are pretty much general to any situation, which is carrying capacity for the prey. Well, there's always a carrying capacity, okay? And some handling time, okay, which always exists. And we can always take the limit where the handling time is very short, and you can just disregard the thing. If handling time is very short, this is always very small here, and then just don't keep it because it's very small. Which you'd say that you go back to the system we just studied, which was Lotka-Volterra with carrying capacities. Okay. Now, this is a system. Okay. Where Mike.
Two questions actually. First one is just that in the predator equation, you put minus dp.
Okay, this is a mu.
Okay.
Just forgotten.
Second question is something you said earlier. You said that when the handling time is 0, the alpha becomes the same alpha as in the first equation.
No, I mean, the alpha is the same. And the way to see this is when the handling time is 0, okay? You don't have this party, okay?
Yes, I understand.
Therefore, you have only alpha p times v, which was actually the alpha that we had before, okay? We had alpha times p times v.
Oh, okay.
Okay?
So in the end, it's the same alpha anyway.
It's the same alpha. Okay?
Okay.
Okay, it's the same alpha.
Okay, thank you.
Yeah. But I mean, it was not a priori. I mean, okay?
Yeah, that's what I wanted to understand.
Yeah, it turned out to be. Okay? Turned out to be.
Why wasn't it a priori the same alpha?
Well, it actually is a little bit difficult. You could have done this saying that handling time is 0. Then you would just say this is 0. The number of queries consumed is a constant times the searching time times v. And then this time to search would be the whole time. And then therefore you would say n over t would be alpha v. Okay.
Oh. Oh, okay.
If I just didn't have this here. Okay.
Oh, okay. I think
Okay.
I'm starting to understand.
So it's a constant connected to the searching time. Okay? Which means that, for instance, the previous equations without the denominator, we had all the time the predator was searching. Only thing that it does. Now, you see also that here, this opens the possibility to do more general things. Okay? More general things would say, no, I want it to take into account some other activities. And then I go on and decompose this in different activities. And this is a way to generate functional forms that take into account more and more things. And one which is typically studied would be the time here at a new time, the time of interference with other predators. So let's say that there would be a situation where there's a lot of predators, and then there's a time for search and time for handling, and then also time for fighting in order to get access to the prey. Okay? It would be a situation like that. So now, this equation, it's much more difficult to study. It's the graphical solutions and so on, graphical methods won't do it. You have to do the math, the actual math. But we don't, because we have a computer. And so we will just explore this numerically. Question, will there be cycles? Will there be fixed points? What will happen? Okay? We want to know. So we go to the computer. We write down. Okay. Okay. We just take the same code we just modify the equation, okay? So let's hope that this will be. So now we have to give new value for, now we have the handling time and the carrying capacity. As I told you, these are arbitrary units, okay? These are arbitrary numbers because these constants have units, actually, okay? And I'm not writing down the units. So therefore, when I say that the handling time is 1, I'm not saying one day, one week, one hour, okay? So, and, okay. So we have some initial conditions, 10 and 3. And we go on, and well, one thing that would be interesting is to see how the solution depends on the carrying capacity. Why? Because, if carrying capacity is very big, if it's like super big, then this should approach something like the Lotka-Volterra system. Because Lotka-Volterra has cycles. Okay, when you don't have the carrying capacity. And we saw that the carrying capacity being small, we have you start the oscillator and you go very quickly to a fixed point. And if the carrying capacity is is large, then what you get is that you oscillate, you go to a fixed point, but it takes a long transient. Okay? So now the point is we have this kind of damping of the oscillations. It's the decaying oscillations come from the mechanisms, which is the carrying capacity. And now what will be the joint result of two different mechanisms, handling time and the carrying capacity? That's the question. So I will put this with a handling time of 1, and then we will go and explore how this depends on the carrying capacity. Okay, so let's run it. And what you get here are stable oscillations. Stable oscillations. And you can look at this here. And that's the phase plane. Okay? Now, let me just see. Let us take a look here and look that this is more or less, here you see the amplitude. So let's modify the initial condition. Remember, with the Lotka-Volterra original system, the period and of the oscillations and the amplitude of the oscillations was strongly dependent on the initial condition, because you got, remember that closed trajectories we had on the phase plane, you got locked into one of them. Now let's try to modify the initial condition. Let's put it 1, 11, no, 1 here, and put 30 here. Okay, so super different. Okay, run it, and okay. Too bad. Problem with 1 and 3. Let's see. I think this would be better. And you get again. And if you pay attention, compare this plot with the previous plot, what you will see is that the amplitude and the period are the same, irrespective of the initial conditions. Okay? So, you see, here I started at this point, and I spiral and go here. Let's say I now start outside this. What will happen? So in order to start outside, let me see, I will put population V at like 8, for instance. This would be like here, okay? Let me put a V which is larger. So now V is the one. Let's put this. So I start outside of that circle, and I run it. I hope it won't be, okay, you get it here, and you run this one, and you start it here, okay, and you go here. So what's happening? It's happening that I start somewhere with a certain condition, and I go and I approach a stable oscillation, but this stable oscillation is the same for any system, any initial condition. And this is much better than the Lotka-Volterra case. Remember, Lotka-Volterra case, if I start with a certain initial condition, I have a certain period and a certain amplitude of the oscillation, and if I change the initial condition, I change also the period and the amplitude. Now, here not. Here you have stable oscillations, and what happens is that with stable oscillations, I approach a certain oscillation with a certain period and a certain amplitude which is not dependent on the initial condition. And this overcomes one of the criticisms that we had about the Lotka-Volterra equation, which was if I have populations that are not connected, they could have different periods of oscillation. And now, they don't, that's not anymore the case. And with this system, you have something which is a preferred period. Okay? Graphically, if you do this running longer time, and the V times P will have some orbit here. It's not a circle, it's anything which is closed, okay? And if I start here, I will go on and approach this thing. And if I start here inside, I will go on and also approach this thing. So there's a transient time, and then we are very close to this preferred orbit. And this guy is called a limit cycle. Okay? So it's not a fixed point, but it's a kind of attractor. Okay? So this is much better. Okay, Mike.
So that means that now we have a stable structure, and if we add a perturbation, it will return to the limit of the cycle.
Yeah. If you perturb this, because the problem with the Volterra was if you perturb it, you change the period and the period stays, like we discussed yesterday with our heartbeats. Okay? You start with 80, but then you run, you got 120, and then you stay with 120. Now this you can be perturbed. You kick it. You kick this guy here. Say you are here, and you kick it because there's something perturbing. Then you get again back to the same. So this is kind of that's what we would call an attractor, really. Okay, the circle. Everything ends up in the circle. The circle. It's not a circle. It's a closed curve.
And what does the null clients look like in this case?
Oh, I can't remember exactly, but I think one is a parabola. It's not even a line. Okay. You have to work it out.
Okay.
I think it's a parabola. And because the null clients now you have this here, and you have to multiply everything by this, gives you a squared here. Okay, so there will be a parabola. And but I mean, working it out now will take time. So now another criticism that we had before to Volterra equation was that everything cycles all the time, and there's no such thing at stable coexistence at fixed levels between predators and prey, which is something that we observe in nature. Everything cycles. Well, we added the carrying capacity, and then nothing cycles. We just have the carrying capacity, and then you go to a fixed point. Now, in the new model, the Rosenzweig-McCarthy, we just find stable oscillations of the kind which we call the limit cycle, which is nice. That's good. But now, we want to know how does oscillations depend on K. So K is the carrying capacity for, where's the equation? K is the carrying capacity for the prey. For the prey is somehow consuming something, and you can think that K represents kind of richness of the environment where the prey lives. If there's a lot of resources, the carrying capacity for the prey it's bigger. If there are very few resources for the prey, then the carrying capacity should be small. Okay? That was all the story about the carrying capacities. So let us So we already know that the initial condition is not very important. We can take whatever we want, because at the end of the day, you go to the closed curve. Now let's see what happens if I modify k. So if I modify k, let's say I will now take, instead of 4, let us take 2. And run it. Fixed point. Between 2 and 4, something happens. If let's try 3, okay? Oscillations, it's difficult to see if they are still diminishing or not. So you would have to go for a longer time and see if they are stable or not. So yeah, it seems that you get oscillations with carrying capacity equal to 3, and with 4 also. But now, remember, with 3, the amplitude of the carrying capacity of the oscillation is smaller than it was with 4. Okay? Look at this here. If you look at that with 4, if you compare it. Okay, this was bad because I did mistake. So the amplitude clearly depends on k. If k is small, with these parameters here, there's a certain point where you have oscillations, and below, for a smaller value of k, you get fixed points. Therefore, the behavior of the qualitative behavior depends on the value of k. There is a certain value of k which we could try to more or less calculate here. I mean, not calculate, try to infer here. So I thought it should be like 2 point, let's start at 2.8. Oops. 2.8 goes to a fixed point. 2.9, but you see, there are oscillations and then you get a fixed point. Let's say 2.9. Oscillations take longer and longer. And with 3, we already came to an oscillation which seemed to be sustainable. Okay, so let's do 2.95 here. Okay, run, and then, well, you would have to run it for a longer time to see if this amplitude is already stable or it's still decaying. Okay, but clearly there's a certain value, which is probably not a simple number. Maybe it's a long number. For k, such that if k is bigger than this value, then you have oscillations, and if it's smaller, you'd have fixed points. So you have fixed points and you have oscillations. Okay? The qualitative behavior depends on a threshold value for the carrying capacity. Super good. Now we have both of them in the same model. Everything depends on the richness of the environment for the prey. Okay? Yeah, obviously this can also depend on the other parameters. You should have to do exploration of the other parameters, what's called the parameter space, which is it's super big here in this case. But you are only looking for k. Okay? So the prediction is now that we can have both. But now let us look at large values of k. We know that with 4 we have a good oscillation, and so on. But now let us look, if I, instead of 4, I just put 10 here. And run it. Numerical errors. Okay. Let's put it 8 and hope. Oscillations that are now sharper But look at this. The prey. Very close to 0. It's not 0, because if it's 0, it could never recover. And then we understand the numerical error. Because numerical error, when I took k equal to 10, there's always a finite precision here, okay? And then probably due to approximations, it got very small number, but negative, right? Because all of this are approximations, numerical approximations, in order to calculate solution. Sometimes you have this, what's called the numerical instability, that comes from the finite precise of your calculation, and then everything. You can work out a better way to solve with different solvers, but you see why it didn't work. But the point is, the oscillations have now very big amplitude, and having big amplitude, and being limited by 0, they come very close to 0. Okay? So we can try with 9, but probably this will also give you. Okay, again, the same thing. You get bigger and bigger, and you get close to 0. If you go back for 4, which was the nice case, the oscillations, well, they also already get close to 0 here. Okay, so you have to do a little bit of like 3.2. So now they are above 0 clearly. So the fact is that this limit cycle here will its amplitude will depend on the carrying capacity. And then think a little bit. We have a certain situation where you could try to do several experiments with different carrying capacities, which you can do with microorganisms, which is it's not difficult, and with different richness of the environment. Then you should have situations where you have a stable coexistence. If you enrich it, you get the oscillations. And you get more and more enrichment for the prey. The oscillations will be very big. And actually, you would theoretically approach the 0. There's no such thing and biologically, that would mean that you would have to have a 1/10 individuals, which is 0 individuals. The system will crash. Okay? Here it doesn't crash when I wrote down with a higher value of k, because mathematically there was not a 0. It was 10 to minus 4. But this is clearly a problem with approximation in this case. And at this level of a very small number of prey being under perturbations and so on can easily make the population go to 0, and they will not recover from 0. Okay? So increasing the richness of the environment for the prey can lead to the extinction of the system. You give it more food, it gets extinct. Okay? And both, because if the prey touches, the oscillation goes close to 0, and the prey goes away, then the predator is a specialist, will also die. So this is called the paradox of enrichment. It's due to this guy, Rosenzweig. Okay? And it's seen as well, it's a theoretical prediction. It's actually not a paradox. Okay? So we could ask ourselves if this kind of situation can be reproduced in laboratory with microorganisms. And guess what? The first person that tried to do something on this line but obviously not looking for the Rosen-Zwijgman card, but looking for the Lotka-Volterra system, was Gauss. In the same book that we already, The Struggle for Existence of Gauss in 34, he went on to study a system which is composed of the paramecium, that was it's a protozoa that he already know, and a predator. And a predator is a guy called Didinium. Didinium is a silicate. Okay, so I have some nice video just to have an idea of what these guys are. Okay, here, let's try. Okay, come on. This is the predator. Okay, and here. So it has this cilia, which is like swimming. Okay, and here he has a protuberance, which is where he actually can prey on the predator, on the prey. Okay, it has obviously it has no way of looking for. It doesn't have eye vision. Okay, so what happens is it goes around. So this is the paramecium. Okay, and actually it's bigger than than the Didinium, but the Didinium is the predator. And okay, that's I have to find more or less where. So the Didinium has the characteristic that because it's kind of swimming, it goes around very quickly, super quickly. So it explores the space very quickly, and anything it touches, it tries to sucks it, consume it. So if you have a sufficiently large density of paramecium, it will at a certain point find the paramecium. Okay, so let's see if we can. So it goes around super quickly in comparison to others, and so there's a paramecium. So he got it, and now it will just get it. So this is the system studied by Gauss. What he found? He found the populations go both extinct, all of this. So he tried to modify the model, but it was not, you see, handling time. Right? And actually sometimes, because the Didinium doesn't know what, it touched something that it consumes, and maybe it's super big, and actually it could happen that the Didinium explodes sometimes. Okay. So he got it. So it's handling time, right? And it's searching time. All of this is there. But honestly, I mean, what Gauss thought that the problem was is that you observed that when the experiment goes on, that actually when there are less paramecia, the Didinium continues to reproduce at almost the same rate, but becoming with smaller individuals. This is not modeled by our models, okay? Something like that is not, because here if the number of prey decays, the number of new predators decays, and that he didn't observe this at a certain range of values. So he said that maybe it's connected to this. He tried to write an equation putting square root of v and so on, but turned out to not be, nobody remembers this. But so he could only observe that at the end, he was trying to see the circles from Lotka-Volterra's original equation, but it's the 30s. He could not find a way to observe them. But it turned out that if when the number of paramecium goes to a small value, and if he artificially pumps in more paramecium, then you see oscillations. But it's a pumped system, so it's not anymore an isolated system. You have to provide more paramecium in order not to have the extinctions. Right? Well, artificial, it's not very nice. But then I also introduced some kind of barrier which the paramecium could, it was not a barrier for paramecium, it was a barrier for the dinium, and then they have the survival of the system because the paramecium had a refuge. A refuge was an explanation. So this stayed as a problematic point, and lots of people tried then to see if they could find predator-prey oscillations. And in the 60s, there were experiments. I think with the same system actually, but introducing spacious heterogeneities or time perturbations. So always with something which is connected to some heterogeneity. Then they could see oscillations. But we have to wait until 1973 and for a paper where actually what the guy did, this is this paper is called by Looking Bill, 1973, coexistence in laboratory populations of Paramecium aurelia and its predator Didinium nasutum. And so it's the same system as Gause. I'm not sure if Gause tried with aurelia or with caudatum. Take a look. And what he found, so you have the medium where you grow your culture, and what? And so this is a certain medium which is it's called. It is a medium which is how it's called. Serrapilheira. Okay, so this is. Don't discuss it. Not so many. That's a medium value, and so you do it, and the population crashes. Well, then he introduced a different chemical element, which is this methyl cellulose, which is a thickener, which makes the solution more viscose. And having a higher viscosity of your environment slows down the movement of the individuals and of the dinion and so on. So then he got something. So here, what is this? He got something like this, okay? Over up to 18 days. You kind of have some oscillations, but the system crashes again, okay? So oscillations, but at the end of the day, the population of Paramecium gets extinguished, and then the didinium also, because it's a manipulated thing, and there are only Paramecium and didinium. Didinium starves literally. So, and you see here, this one is the aurelia, and it goes to 0 here. This thing is probably wrong. It's to 0, and then this one gets there. So crashing. Again, you have the crash of the population, but you have oscillations. So this looks like this could be connected to the Rosenzweig-McArdle system, where you have a rich environment and you have the oscillations, but after some oscillations you get so close to population equal to 0 for the prey that it gets extinct, and then everything collapses. So idea, let's have a less rich environment and see if oscillations can go on longer if I just have a poorer environment for the paramecium. And what you do is, instead of using the usual environment, the environment is this cetaphil with some bacteria, because paramecia consumes bacteria. Okay? So, and the idea is, okay, let's put half of the bacteria. So let's make the paramecium have a smaller, a poorer environment. Therefore, the carrying capacity for paramecium, which actually he measures also the carrying capacities, because you can grow the paramecium without the didymium, and then you see it goes to a certain carrying capacity. So he just tried to lower the carrying capacity and see what happens. And then he got actually many attempts, he got this one. 33 days of stable oscillations. And after 32 days, it just terminated. It could continue, but I mean, they say, okay, we are convinced that these are stable oscillations, and they just ended the experiment. Okay. So, stable oscillations, and this is more or less what we have here. Smaller carrying capacities, not too small, because I mean, if you take a very small one, you got a fixed point. Okay, but this he didn't try. Well, but very large, big carrying capacities, too rich environment, the oscillation have very, very big amplitude, and the big amplitude should approach the zero population. Under any perturbations, you get extinction, and then you have the system crashing. But if the carrying capacity is at a certain value, intermediate value, such that the oscillations don't take the system too close to zero population, then you have the oscillations which are predicted by the Rosenzweig-McCarter equation. Okay? So the fact that they have a limit cycle and so on was not studied by this guy. This paper is important in the sense that he could, in a homogeneous medium, without introducing refugia, without pumping new individuals from time to time, just the system, homogeneous system, without what they called physical complexities, could have oscillations of the kind that are predicted by the Rosenzweig-McCarter equations. Okay? So this is very nice. So we have some reality to the model, and actually the Rosenzweig-McCarter is the main model of predator-prey dynamics. Well, it is at least the starting point for more realistic models. Okay, you could go for other phenomena like interference of predators and so on, which could be discussed in this and could be discussed by doing different functional forms. But so the basic model for predator-prey relations, which has a minimum of realism, is the Rosenzweig-McCarter. So, any questions about this? We are already approaching the time. Yeah.
I'm thinking about the biological meaning behind this paradox. Like, biologically speaking, what exactly caused the extinction of the paramecium?
The extinction of paramecium is that the amplitude of the oscillation, the population, increases a lot. Okay? Increases a lot, but this also feeds a lot of predators. Okay? And predator population gets a lot of prey, consumes a lot of prey, and depletes the number of prey. But it goes to such a small level of the population of prey that actually what happens is that here the model does not predict the extinction, but predicts a very small value of the population, which biologically is a zero. Okay, something very close to zero, 10 to minus 10 individuals is mathematically not zero and can recover. But 10 to minus 10 individuals. Biologically means zero individuals, because you don't have half an individual, but you have half individuals only mathematically. So that approaches the limit where the description here is not anymore. I mean, you should always interpret the mathematics in biological sense. The biological sense is that something very close to 0 is 0. Okay? And actually, what happens is the Didinium eats all paramecium at a certain point, but there are so many paramecium, and it's able to eat all of them, and then there's no paramecium, and the Didinium will die starving. That's it. Any more questions? Okay, so that's all for today. So tomorrow is question and answer and discussions. So you can write down the box is disappeared. Okay, there should be a box there. Where's the box? Oh, that's. Nobody actually used this. That's. But if you want, you can write down your questions. If you don't want, you don't write. And so tomorrow, again, discussions on interacting species in general. Okay.